And so here I have sort of a description of how you get the bonding orbital formed. And so let me just kind of focus on that. And so here in this slide, what you can see is we have these two 1s orbitals here, and we're going to add them, much like we did in that prior description I explained. And then when you add them, you form the bonding orbital. Now, the thing I want you to notice now is that this is drawn out on an energy diagram. So notice that energy or potential energy is on the y-axis. And so what you'll see is that this new molecular orbital you get by mixing these two 1s orbitals constructively has a lower energy than the atomic 1s orbitals have themselves. And so that is important to keep in mind. Whenever you have bonding orbitals and if there are electrons in them, they will have a lower energy than if the electrons were in the separated atomic orbitals themselves. Now here's where I describe the formation of the antibody orbitals. And so this time what you do is you take these 1s orbitals and you subtract one from the other, much like I did in the diagram. And so you create that antibonding orbital. Now note there are different colors for the antibonding orbital. So all the different colors do is indicate that, like I showed you on the graph, there's a portion of the function that was in the negative zone compared to the other side of the hydrogen atom where the function was in the positive zone. And so we tend to indicate that with a different color. But in the end, both the positive and negative zones were squared. And so even though they're different colors, those are both electron densities that are equivalent basically around the two different nuclei, and you're just as likely to find electron in that red electron density as you would in that blue electron density. And it also nicely shows you the region where you cannot find electrons, which is between the nuclei, the nodal plane. Now here, important to know again, is what we have is we've described this process of forming the antibonding orbital on an energy diagram. And you can see that the antibonding orbital has higher energy than the individual atomic orbitals it came from, which means is if you have electrons in the antibody orbital, they will have a higher energy and be more unstable than, say, if you had electrons in the individual but separated atomic orbitals. And so here is the total picture. And this makes the point that if you have two atomic orbitals you are mixing, you're going to create two molecular orbitals. One by constructive interference, which is the bonding orbital, and one by destructive interference, which is called the antibonding orbital. Okay, so there's another way you can sort of represent this process, and here it's done on the left side, is through orbital notation on an energy diagram. So if you look here on the picture of the diagram here, what you'll see is that you will have a box there on the far left. And this box here on the far right are the atomic orbitals that the molecular orbital is derived from. And so what you can see is that here in this notation, what we're showing is how the two molecular orbitals form. And so the two molecular orbitals are here. This lower orbital here is the bonding orbital. I've got a blue box around that. And the antibonding orbital is above it, which I have a red box at. And also I want you to know is that they're given names. And so here in the bonding orbital in blue, you can see the name or designation is given. It is a sigma 1s molecular orbital. So the reason why it's called a sigma orbital is because the electron density is equally distributed around the axis between the nuclei, as we were talking about before with other orbitals. Now, how about the antibody orbitals? You can see the designation is similar. It is sigma 1s, but there's an asterisk here. So let me circle the asterisk. And so the asterisk just reminds us that this molecular orbital we're looking at is an antibonding orbital. Okay, so what I want to do is I want to sort of get used to how do you find electron configurations in something called bond order for simple molecules like hydrogen and helium? So here, what I'm going to do is I'm going to use this orbital notation here to sort of describe how you form the hydrogen molecule from the individual hydrogen atoms. And so what you sort of see right now is that imagine you have two hydrogen atoms that are kind of far away from each other. And so one electron is in the left hydrogen atom, and it's in its 1s orbital, which you can see there. And then the right hydrogen atom, which is kind of far away, has its 1 electron as well. Now let's say you bring them together and they form molecular orbitals. Where do the electrons go? So we're showing that next. Both electrons will go to the lowest energy orbital that's available to it. And so what you can see is that the bonding orbital has less energy than the antibonding orbital. And so for that reason, both electrons will go there first. So this is very reminiscent of the Aufbau principle with electron configuration of elements, in that the electrons always go to the lowest energy of orbital that's available to them, and that you can have a pair of electrons going into the orbital, which we see here. So it's just like that. Okay, so now what I want to do is I want to try to answer a few questions, which is, what is the electron configuration for H2, and what is the bond order for H2? So let me bring up this next slide, and I'm going to go over to the light board. Okay, so we want to find out what the E configuration, get a better pen here. We want to try to figure out what the electron configuration for H2 is. And then also we were going to try to figure out something called bond order for H2. So let me talk a little bit about how you go about doing that. Okay, so what we're going to do is we're going to look at H2. And so when we figure out the electron configuration, all you really have to do is look at the valence electrons. And so with H2, we know it's atomic number 1, and so there's only 1 electron in hydrogen. It's in the 1s orbital. How many valence electrons does a hydrogen have? Well, at 1 electron, the highest energy level is that 1 valence electron, so there's 1 there. So each hydrogen atom here has 1 valence electron, right? But then it's going to be bound to another hydrogen atom, which has 1 valence electron. So we have 2 valence electrons we have to deal with. So from these 2 valence electrons, what we have to do is figure out the molecular orbitals that these 2 electrons go to. So one bit of a memorization you're going to have to do is you're going to have to remind yourself what are the molecular orbitals that these 2 electrons can go to. So the way you remember that is you think about 2 hydrogen atoms. And so you're imagining 2 1s orbitals sticking together. And from those 2 1s orbitals, they will disappear. And then you'll create 2 new molecular orbitals, the bonding orbital and the antibonding orbital. Now, what I'm going to do is I'm going to write an orbital notation for those orbitals. I'm going to do it in a little bit of a different way. So remember back in the olden days, what we used to do when we were writing out orbital notations, we would write them out in a horizontal line, like I would have S here, and then I would have P's and D's and so on like that. So that worked perfectly fine when we're considering the electron configurations of elements. But here now we're looking at the electron configurations of molecules. And what chemists like to do is they like to write out the orbital lines vertically. So going back to the problem H2, what are the molecular orbitals that form? You have 2 atomic orbitals, 2 1s orbitals that mix together. You form 2 molecular orbitals. One is a bonding orbital, so I'm going to draw this here. I'm going to call it sigma 1s. And then one is an antibonding orbital, which I'm going to draw here, which is sigma 1s with an asterisk. So here we're drawing vertically, and we're imagining here that the y-axis is now energy. Okay, now we have 2 valence electrons in hydrogen. Where do they go? So again, they will fill up the lowest energy orbital that's available to them, so they go to the sigma 1s orbital. So that's it for H2, hydrogen. What is its electron configuration? Well, what you do is you somehow have to note we have 2 electrons in the sigma 1s orbital. So what we write here is sigma 1s, and then we put this in parentheses, and to indicate that there are 2 electrons there, we put a 2 up here. And so this is the electron configuration for the H2 molecule. Now the next question is we're going to figure out something called the bond order. So let me talk about how you calculate that. We'll calculate it for the H2, and then we'll interpret it a little bit more from there. So what the bond order of this molecule is calculated from a simple formula, which I have on the slide there. The bond order is going to be equal to 1/2 the number of electrons in the bonding molecular orbitals minus the number of electrons in the antibonding orbitals. So let me go ahead and calculate this. So first off, how many electrons do we have in the bonding orbitals? How do we identify the bonding orbitals? The bonding orbitals are the ones that don't have an asterisk. So here we have 2 electrons here in a bonding orbital. Now, how many electrons do we have in an antibonding orbital? Those are the orbitals that do have an asterisk. And so we have no electrons here. So we have no electrons in the antibonding orbital. And so what we do is we take this number and divide by 1/2, and you can see that the value for the bond order for the H molecule or H2 molecule, the value is 1. Now, what is the interpretation of bond order? Well, the bond order is sort of a numerical value that tells you the number of bonds that can be between 2 atoms. And so we know from the Lewis structure of hydrogen that we might expect a single bond between the 2 hydrogen atoms. And in fact, the bond order, when it's an integer, that should match the number of bonds that you see in the Lewis structure. And so the bond order is 1, and so we would expect a single bond between these 2 hydrogen atoms. And so that is also what is predicted in the Lewis structure. Now, you'll get into other molecules where you do that same calculation, and you'll find that for another molecule, for example, like with oxygen, you will find that the bond order is 2, which matches the fact that from a Lewis structure, the 2 oxygen atoms are held together by a double bond. With nitrogen, you do the calculation, you'll find the bond order is 3. And when you do a Lewis structure for the N2 molecule, you'll find that there's a triple bond between the 2 nitrogen atoms. Now, the thing that you will also see is that you will have molecules that you'll calculate the bond order from, and they will not have an integer value. They will have a fractional value. It may be something like 1/2, or it could be something like 3/2 or 5/2. You'll see that quite a bit. If you have a molecule that has a bond order of 1/2, needless to say, it probably is not going to have a full bond between the 2 atoms, right? There's maybe only going to be 1 electron that is between the 2 atoms. So that's something that is a possibility. You may have a molecule with a bond order of 3/2, and so you would not expect 1 bond with 2 electrons or 2 bonds with 4 electrons between the 2 atoms. What you would expect is maybe that there are 3 electrons between the 2 atoms. That's a possibility. So be prepared to see bond orders that are between integer values. Okay, so what we're going to do now is we're going to go on, I'm going to go back to the computer, let's do another one of these. And so here what I want to do is I want to talk about how is it that maybe we could form diatomic helium, in other words, 2 helium atoms bound together. So here I'm describing how this process may occur. And so what you can see on the left side, maybe we have a helium atom with its 2 electrons, and then on the right side we have another helium atom, a different one, with 2 electrons. And let's say they get close together. What happens according to molecular orbital theory? Well, what will happen is these two helium atoms, when they get really close together, they will get rid of their atomic orbitals, and what they'll do is form two molecular orbitals. One of them is going to be a bonding orbital and one's going to be an antibonding orbital, and you can see them there. And so what will happen is two of the electrons from these 1s orbitals of the helium atoms will go into the bonding orbital, and we have two left. And the other two electrons go into the antibonding orbital. And so now basically what you have here is the configuration for diatomic helium. So now we're going to look at diatomic helium on the glass board. And so let's go ahead and figure out an electron configuration for diatomic helium, and then we're going to figure out what the bond order is. Okay, so how do we figure out an electron configuration for diatomic helium? So you might recall that helium is atomic number 2, and it has 2 valence electrons. And another helium atom also has 2 valence electrons for a total of 4 valence electrons. Now, we have to figure out the orbitals that these 4 valence electrons go into. So again, you have to remember what the molecular orbitals are that these electrons can go to. And so what you might remember is when you have 2 1s orbitals mixed together, you create 2 molecular orbitals. One is the bonding orbital, which is called sigma 1s, and one is the antibonding orbital called sigma star 1s. So let's talk about where these 4 electrons go. Well, 2 of the electrons will go into the bonding 1s orbital, and then the other 2 electrons will go into the antibonding 1s orbital. So how do we write out the electron configuration for diatomic helium? So the way you write that out is you write sigma 1s squared, and then you have to include the antibody electrons because they're in the configuration, which is sigma 1s star for antibody squared. Okay, now one thing you may already know is that diatomic helium does not exist. So we need to maybe look at the bond order and see how many bonds can form between a putative diatomic helium molecule. That may give us a clue as to why the diatomic helium molecule cannot exist. So let's go ahead and figure out the bond order. So the way you figure out the bond order is that you have 1/2, and then you look at the number of bonding electrons, and there are 2, and subtract from that the number of antibody electrons, which are 2. And so 2 minus 2 is 0, divided by 2 is 0. So you can see the bond order for diatomic helium is 0. What does that mean? It means that it is predicted between 2 helium atoms that you would have no bonds form between them. And so you would never get them bonded together. So we can, if the bond order for a molecule is 0, it predicts that those atoms will never get together to form a molecule. Now there's another way of looking at it, and which you need to know, which is sort of looking at the slide there. And so what you're going to see is that here, when you form the He2 molecule, 2 electrons are in the bonding orbital, which has a lower energy than the atomic orbitals that it's derived from, and 2 electrons go into the antibonding orbital, which is going to have a higher energy than the atomic orbitals that it's derived from. And so basically, when you stick these 4 electrons into these 2 molecular orbitals, the energy averages out. And you can imagine that the energy, that average of the energy between the antibody orbital, which is relatively high, and the bonding orbital, which is relatively low, averages out to be the same as the energy that the electrons would have in the atomic orbitals. That means is that there's no reason for these electrons in the atomic orbitals to form a molecular orbital, because if the electrons go into the molecular orbitals for a diatomic helium, they will average out to have the same energy that they would have if they were in the atomic orbitals. So there's no reason for the electrons to go into molecular orbitals. They have the same energy. If they have the same energy, they will have the same stability, and so the molecule is not likely to form. Okay, so we'll do one more problem here. I'm going to go back to the computer. And so what I want to do is I want to show you how we can understand how the electrons go into bonding and antibody orbitals when you form a diatomic helium molecule that is missing an electron that therefore has a positive charge. And so here is an example on the computer. And so on the left side of this picture, we have a regular helium atom, and it has 2 protons, I'm just mentioning that now, and 2 electrons. And then on the right side of the diagram, we have a helium atom. It has 2 protons like the atom on the left side, but it only has 1 electron. And if so, it is a helium atom, but it's missing 1 electron. It is a positive ion. So what we're going to do is we're going to smush the helium atom on the left with the helium ion on the right, and we're going to create the helium-2 plus molecule. And the way we're going to do that is we're going to put or create a bonding and antibody orbital from these atoms and ions and see where the electrons go. And so what you can see here, when you form the helium-2 plus molecule, you'll create the bonding and antibody orbital. And you'll note of the 3 electrons, 2 of them go into the bonding orbital, and then the last electron goes into antibody orbital. So now from here, I'm going to go back to the light board, and we're going to talk about what we can expect the electron configuration for the helium-2 plus ion to be, and then what the bond order is. So let me work that out on the glass board now. And so here we're going to work out the electron configuration for the helium, diatomic helium molecule that has a positive charge, and then we're going to work out the bond order for this molecular ion. Okay, so here we have 1 helium atom that has 2 electrons. Now, the way you can sort of figure it out in terms of electron configuration is you can point out that, or you can remind yourself that the other helium atom has 2 electrons, but because there's a positive charge, let us subtract 1. And so now we're down to 3 electrons. And so we have to predict where do these 3 electrons go in these molecular ions, molecular orbitals. And so here is a bonding sigma 1s orbital, and here is an antibody sigma 1s orbital. And so of the 3 electrons, 2 of them will go into the bonding orbital, and 1 will go into the antibody orbital. And so what will be the electron configuration for the helium-2 plus molecular ion is going to be sigma 1s squared, or 2 for 2 electrons, and then sigma star, the antibody orbital here, 1s1. So that is the electron configuration for this helium-2 plus ion. Now, what is the bond order for this molecular ion? So it's going to be 1/2, and then what we're going to do is count the number of bonding electrons here. There are 2 there. And then what we're going to do is subtract from it the number of antibody electrons, which is 1. So if you do that calculation, the bond order you should find is what? It's going to be 2 minus 1, which is 1, times 1/2. The bond order should be 1/2. So what does that say about this molecule? What it says is that this molecule does not have a single bond. Instead, it's something in strength between a single bond and having no bonds at all. And so we'll stop right there. We will continue on next time with another talk, and this time we'll look at molecular orbitals for elements in the second period. Thank you for listening.